Good morning, good afternoon, good evening. My name is Fiona Case. I'm a Scientific Communications Manager at AOCS. I'd like to thank you for joining us for this special edition AOCS meeting webinar. The topic for our discussion today is online FTIR analysis for process control of biofuel production. Our speaker, Jonathon D, is a Product and Applications Manager at Keit Spectrometers in Didcot, United Kingdom. He received both his master's and his doctorate in chemistry from the University of Southampton in the UK, and he is a chartered chemist. He has authored multiple publications in the field of vibrational spectroscopy. Dr. Speed's areas of expertise include nanotechnology, particle and colloid characterization, and the use of FTIR, which of course is Fourier transform infrared, and Raman spectroscopy in materials analysis and in situ characterization of processes. He has published 8 patents in the field of surface science. Please write any questions for our presenter in the questions section of your control panel. All questions will be answered at the end of the presentation. And with that, I will pass over to our presenter.
Thank you very much, Fiona. So thank you all for attending. I'm delighted to be talking to you today. I'm going to talk about the fundamental technology of how one would use FTIR for this type of application. Go through some of the basics of what makes this spectrometer a bit different to some others, and then go to look at some technical results towards the end of today's talk. So I'll start off with, it's almost a cliched slide, I do apologize, they pop up everywhere. But who is Keit? What is the company I work for? What do we do? As was said in the introduction, we're based in Didcot, which is here just south of Oxford in the United Kingdom. And we're a spin out from a UK government research centre originally. And that centre used to do a lot of analysis on nuclear physics, and nowadays it's moved towards into space science. And it is effectively the UK's hub for space technology. And one of the things that that department was actually looking at was doing spectroscopy of the atmosphere of Mars. So developed a spectroscopic concept that could go to Mars and could take measurements of the atmosphere. And of course, if you're doing that, you need to survive launch. You need to survive travel to the planet, and you can't have any service engineers go to Mars and visit to do any repairs. So it has to be robust and reliable. That core technology would then spun out to be the basis of Keit Spectrometers. So there's a lovely photograph of our building there, and that's who we are. So we make a static optics spectrometer, and I'll talk a little bit more about what that is in a bit. So some background, foundations. Industrial revolutions. We're all quite familiar with the concept of an industrial revolution. The Industrial Revolution, the first one, the famous one, happened in the 18th century, and that was mechanization. That was the beginning of that was the steam engine. It was using machines to automate processes without any interference from humans. So something that could be fueled and allowed to run by itself with no animal giving it any energy. After that came the second Industrial Revolution. This was the mass production. This is Ford and the motor car and the production line, and being able to, rather than making one thing at a time, start to make multiple things either sequentially or in parallel, depending on how these production lines are set up. And electricity became a key part of that, using electricity to drive processes and make them faster, more efficient, more productive. After that, we had the digital revolution, which is the third industrial revolution, which was the advent of computers and electronics, and being able to start using computers to automate processes. So you can have something pre-programmed that sits there, it knows what it's doing, it runs the same thing again and again and again. And that was the second half of the 20th century. And we are now in the fourth industrial revolution. The catchy name is Industry 4.0. And this is taking everything that was built in the third industrial revolution and taking it to the next level. So this is robots, cyber physical systems. So systems that have advanced sensors and advanced algorithms and computer programs, and using that along with the digitalization of data in order to make decisions on the fly in a computer and enable real-time, it's called closed loop control. So take a measurement, decide what that measurement means, and take an action in the space of milliseconds. An obvious example is in something that's heating, a distillation column, for example. If you've got a distillation column and you want it to maintain a constant temperature, well, the way we do that is we feed in fuel, and the fuel burns or steam heats a column up, and that generates the heat inside it, which drives the process. But depending on what you're feeding into it, that fuel then has a different efficiency. And if you're feeding in something cold, a lot of the heat will be taken out to heat up the liquid itself, and the column will cool down. If you're feeding in something hot, you won't need to take so much heat out, and the column will stay hot. So you need to make that measurement. What temperature is your column running at? That then feeds back into a controller, so it knows how much fuel to feed in to keep the constant temperature. So even something as simple as effectively heating a bar is not as trivial as we think it is. And that's where things like Industry 4.0 become really powerful, because they allow much, much tighter standard deviations, much higher efficiency, and improved processes. We're at that point. But if you want to really use Industry 4.0, and in this case, we're talking about biofuel and renewable fuel production from predominantly triglycerides, how do you actually make a decision? You need to be able to analyze something, which means you need to be able to look at your process, look at your chemistry, look at what is happening, and use that information to make a decision to drive that change. There's a famous quote from Lord Kelvin of that which is measured gets improved. So you do need to be able to measure something in order to make that improvement. And there are a few different ways this can be done. So on the left of this diagram, we have simple online measurements. So pH measurements, temperature measurements, we do them all the time. pH probes are not expensive. Temperature probes are even cheaper. Temperature probes are absolutely everywhere. They are all over processes, as they should be. Flow meters as well. They measure one thing, and they measure one thing very well. They do a very good job of that, and they give you that one piece of information, and you can use that to infer what's going on. At the other end of this graph on the right, we have offline measurements. These are things like HPLC measurements, or AES measurements, or chemical assays. Titrations is a good example of this. They go into more detail. They often directly measure the chemical you care about, but they're not in real time. They're expensive and they're slow. It's a bit like using a sat nav. You don't want to use a sat nav. You're driving your car and it tells you 5 minutes ago you took the right turning. Or even worse, 20 minutes ago you turned left where you should have gone straight on. That is not helpful. At that point, you've got to row back. You've got to go back to where you were before, go the right way. So offline information gives you the info you need, but not necessarily the time that you need it. And then in the middle, we've got spectroscopic measurements. These are real time, much like the online ones. And they, depending on the technique you use, can look directly at the chemicals you care about. So it's effectively the best of both worlds. It is directly looking at chemistry in real time. And that is where the power comes from. And this is the way you would normally use a sat nav. At the end of the road, turn left. You get told before you need to make that decision, and it's helpful. So if this is so wonderful, why are we not all using it right now? It's the barrier to entry. There is always a barrier to entry. Nothing is easy in this real world. There's always a little bit of work that needs to be done. Spectroscopy requires a calibration. That's a fact. Calibrations can be painful or they can be relatively painless. And that depends on picking the right technique for the process you want to measure and calibrating it in a sensible way. So the way we calibrate these processes, or the way we calibrate spectrometers for these processes, the first thing we do is we get our calibration spectra. That can be done in the laboratory. It can be done online. It can be done a bit of both. That's my preference. Take some samples in the lab, spike them with some known chemicals you care about, mix them up a bit, we call it a calibration set, a set of samples, analyze them all really quickly, get through them in the lab. Then take your instrument online, actually install it where you care about, and take some grab samples. That way you get a bit of both. You can make some variation in chemistry very quickly in the laboratory, but you can then sample the things that you see online. So pressure, temperature changes, all the little things. Sometimes you take a sample offline and there are chemicals that exist there that go off, intermediates, transition states, chemicals that do not last very long once you take them out of the process. But you see those online. So I personally think it's really important to do both. We then take our reference concentrations. From the lab, this is easy. We know what they were. We made those chemicals up ourselves. Online, we need some kind of reference technique. And that's where the offline data I was just talking about becomes useful. So something like an HPLC measurement, a titration, if you're looking at things like free fatty acids. If you want to do phosphorus levels, you might put them through an atomic emission spectrometer. If you've got an NMR machine, you might use that, although they are really expensive. But that kind of offline analysis to get that data. Then you build a model. There are simple models, very simple models that are just straight line regressions of one data point versus your concentration. There are more advanced models that are called partial least squares that are basically a linear regression, but of the whole spectrum. It's a linear regression where we use a matrix instead of one data point. And then at the other end, you have very advanced calibrations like support vector regression or artificial neural networks. That's machine learning. That's artificial intelligence. As an aside, there is nothing artificial or intelligent about artificial intelligence, but it is artificial intelligence. We train it, we tell it what to do, we feed a lot of instructions in. It's very, very prescriptive, but it allows you to pull out nonlinear calibrations, and it's incredibly powerful. But if you're doing that, you have effectively a black box. You don't know what the algorithm is doing. So you have to validate, and you validate your model. And you do that by throwing in data it's never seen before. And you ask it to predict what the concentration is, and then you validate that. Was that the right concentration? And we see examples of that all the time. Machine learning algorithms look at things like pictures on Google and Facebook and things, and then they'll throw in a picture of a dog and say, what is this? And if it says dog, you know it's working. If it says cat, you know it's not. It's the same kind of thing, but for chemicals. So there are lots of different types of spectroscopy. I'm going to very, very briefly, and this is as quantum physicsy as this gets, I do promise, just talk about a few different types of spectroscopy. So this is called a Jablonski diagram. You may have seen these before, you may not, don't worry about it. Basically, every molecule has energy levels. Molecules have energy, and we know this. When you heat things up, they get hot, they take energy in, then they emit that energy and they cool down. That's predominantly infrared, but infrared light is only a small part of the wavelengths and the spectrum of light. So infrared happens to sit just outside of what humans can see. There is a bit called near infrared, and you can tell from the name. The near means it's close to what humans can see. We have visible light that humans can see, and then we have UV, which is the other side. So that's the shorter wavelengths of light that humans can't see. But there is near UV and far UV and all of that. So depending on the wavelength of light that we use, different things happen. If we use UV vis light, so UV and visible are close enough that we tend to group them together, what we see is the molecule gets excited from this ground state up to what's called an excited electronic state. It just means it absorbs that energy and it becomes excited. And it's quite a big step up on this kind of energy level. Mid-infrared does exactly the same thing, but at a different scale of energy levels. So we have electronic states for UV vis from the ground to the excited, whereas infrared is all about vibration. And that's the vibrating chemical bonds. So a carbon-oxygen bond vibrates at a given frequency. Carbon-hydrogen bond vibrates at a different frequency, and so on and so on. And by taking in that energy in the mid-infrared, what happens is we cause that vibration to become excited, and it vibrates more. More of the atoms, the bonds, sorry, inside the molecule become vibrated, and they have more energy in that state. Near infrared is the similar type of thing. It's still vibrational states, but you jump up 2 or 3 at once, or a combination of them. So mid-infrared is, we call it the fundamentals. It's always 1. From this up to the next one. It's very, very easy to interpret because it's very simple. Near infrared would either be, and this is called the overtone because it's the same energy transition, but it's we jump 2 at once. So this will be the second overtone, this will be the third, or it's a combination. So if you look at something like a sugar molecule, you might have a carbon to oxygen bond and a carbon to hydrogen bond, both vibrating at once, and that's a combination. It's very difficult to understand what's going on there. It's a bit like trying to walk upstairs. If you want to count the number of stairs, the easiest way to do it is to walk up one at a time. And you count the steps, you know exactly how many you've got. With near infrared, it's a bit like running up them. Sometimes you'll take 2, sometimes you'll take 3, you're not quite sure. Very difficult to count how many steps there are if you do it that way. You still get to the top, but you don't have that granularity of data. You don't know how many steps there were. Then there's this other thing off to the right called Raman. Raman gives a similar kind of information to infrared. You can see the gap between here and here is still 1 rung on this ladder. So it's the same distance, same type of information. But this is done using a laser, and we excite a molecule up to what's called a virtual state. It doesn't actually exist. And then it collapses back down, and 1 in every million photons of light will cause this to happen. The other 999,999 will do this. Rayleigh scattering, absolutely no change. Shine a light on it, and it bounces off with the same wavelength, no change. Raman, you may have heard about, is not really suitable for the edible oils industry in particular because of something called the selection rule, which I've got on here. So the Raman selection rule has a very posh definition, which is there must be a change in the polarizability of a molecule as a function of nuclear displacement, which means as the bonds inside the molecule vibrate, the electrons have to be able to slosh about, and they have to be able to move throughout the molecule as it's vibrating. If you look at the structure of a triglyceride, we've got the very highly polarized bonds in the carbonyl group of the ester. In a fatty acid methyl ester, it's the same thing, just without the glycerol group. We've just got the discrete methoxy groups. Alcohols, polarized charges at the end in the alcohol. A lot of these molecules, phosphorus, phosphates, if you're looking at that, I'll talk about those in a minute. Phosphates, highly polarized. They're not really very good for Raman. The selection rule, you could probably make a Raman instrument work, but you'd be trying very, very hard, and you'd be throwing an awful lot of effort at it when there are other technologies that just do it naturally. UV-Vis looks at a different bit of the spectrum. So UV-Vis is great if you want to see carotene or chlorophyll, which I appreciate are useful in edible oils, for example, not so much in the fuels. Because of the way the structures they are, the reason why carotene is bright orange is because it gets electronically excited by light. UV, visible, bright colors, green and chlorophyll, these are all linked. It kind of makes sense when you step back from it and think about it that way. You can, however, also look at chlorophyll or carotene using FTIR because those molecular bonds also vibrate. So FTIR, NIR, they've got a lot of benefits in this type of industry because they're looking at the fundamental data that we want to see. So we've compared Raman and UV-Vis with NIR and FTIR, comparing NIR and FTIR themselves. It's like I just said about coming up the staircase. Is it better to walk up one at a time, or is it better to jump up in 2s and 3s? Depending on what you want to know. If you just want to know, is it a long staircase or a short staircase, then do whatever's easiest. If you want to know how many steps are there, you need to count them one at a time. NIR doesn't have the granularity of data that FTIR does. So another example, NIR would give you this level of information. Is this picture a vase, or is it 2 faces looking at each other? It gives you the shape, it gives you a rough idea of what's going on, but you don't get anything else from that. FTIR can tell you it is clearly a vase. So in the edible oils and the fats and oils and grease sector, an example, palmitic, stearic, oleic, those acids, FTIR can pull the difference apart because it can look at the ratio of carbon to hydrogen bonds to carbon-carbon bonds. And that changes as the acid chain length changes. NIR would probably struggle to separate those out because they're too similar. And then linoleic and oleic acids, again, NIR will probably do a reasonable job of telling you there's a double bond there. But if you wanted to start looking at cis and trans acid, unsaturated acids, it wouldn't be able to tell that difference, whereas FTIR would. So it's that kind of difference that we talk about. There's one other thing about NIR instruments that's worth remembering, and that's the design of the probe. So all these instruments have a probe. They have to. You have to get the light into your sample somehow. FTIR instruments have what's called an ATR probe on the left. And it's called the evanescent wave. So there's a little bit of light that escapes the probe, just a couple of microns, and sits into the solution. And that interacts with your liquid. Doesn't matter what that liquid is. It can be aqueous, it can be an oil, it can be a slurry, an emulsion, doesn't care. It interacts with it, and that's what makes the measurement. And it doesn't really care about solids. The amount of light that interacts with the liquid is huge compared to the solids. So it doesn't really see them. And the same goes for bubbles. Doesn't really see them. Over time, you average them out. So the intensity of a peak is proportional to the path length. So the amount of light that goes through the liquid. The bubbles are transient, they're moving. So they average out, and then you can normalize for them as well. So they're really not a problem. What this does mean is you probably can't measure the solids. So if you were looking at something like a fermentation, trying to measure biomass using this technology, probably not going to work. It's not designed for that. But what it does mean is as your biomass changes, and if you're using a classical fermentation where you're growing yeast in the first step, well, it doesn't matter that you're growing yeast in the first step. The spectrometer is going to carry on working as that yeast grows. Whereas other technologies, NIR and Raman, can have massive issues with that because the particles get in the way. And that's an example on the right-hand side. NIR instruments they're either called transflectance, transmission, or reflectance probes, depending on which marketing spiel you're looking at. But effectively, light has to go from a surface to another surface and back again for them to work. Sometimes there's a sensor here rather than a mirror, but effectively we've got to go across this path. That's how they're supposed to work. The second you add particles or bubbles, you get refraction and diffraction, and it becomes much, much more difficult to get a meaningful amount of light back in again, which means you have to start adding in extra layers of maths to get anywhere. Your error bars get larger. It becomes much more difficult to make a measurement. So one phrase I hear quite a lot is, oh, we tried an IR, it doesn't work. I wouldn't necessarily disagree with that. But what I'm talking about today is FTIR, mid-infrared, not NIR. So I appreciate I'm laboring that point, but I'm trying to make sure it gets driven home because they are fundamentally very, very different. So the thing I want to talk about, it's about 30 centimeters long. It's got an armored shell, 24 centimeters wide. It's got a sensing probe. And when we made it, we thought, well, what else has a sensing probe about the same size and an armored shell? And we came to the conclusion it was an armadillo. So everyone has to have a pun on the word infrared if you work in our industry. So our product is called the IR Armadillo. I've not actually had the honor of seeing an armadillo in the wild yet. I hope to come out to America at some point soon and be able to see one. But that is what we make. And just to show you, this is the ATR here. It's just a piece of diamond that just does the sensing. So that gets installed directly into the process. So how does it work? How does it work, and then how do we go on to use it? There is an emitter, which is here. It's actually, we've just moved it back to here in the body of the spectrometer, which means it's much more thermally stable. So we can now run at 230 degrees C, I think it is. It might even be 240, with no impact. Even though infrared is heat, we don't care. We've shielded the emitter from heat. That light then comes out into our ATR, interacts with the sample, and that's where the absorption of the sample happens. So that happens the first thing that we do. Then the light goes back into the body of the spectrometer and hits a beam splitter. If you've ever had your head resting on a window and you've looked on a bus or a car or a train, and you can see your reflection, but you can also see through the window, that's a beam splitter. That's exactly what happens here. So some of the light gets reflected and goes around this track of mirrors, and then it gets reflected off the beam splitter and hits the detector array. The rest of the light goes straight through, goes around this track of mirrors clockwise, comes back and hits the detector array here. And they are slightly offset to each other, only ever so slightly. And that creates an interference pattern on the detector array. That interference pattern is not a spectrum, but we can collapse that down and do what's called a Fourier transform on it. And that's the FT in FTIR, as Fiona said earlier. That creates a spectrum. That spectrum can then be interpreted to give you chemical concentrations using the calibration I spoke about earlier. And there you go. So we're now back at the point where we've now got meaningful chemical concentration values. Then we can actually act on that and do something with it. Just to show you some photographs of the instrument installed to give you an idea of what it looks like. It's about the size of a shoebox. It's a large armadillo. And it's a very heavy shoebox, but it is a shoebox. Here, this is actually in a paper mill, which I appreciate is not biofuels, it's not oils, but it's a good example. It's in a paper mill in Sweden, and they are measuring highly caustic materials. This is pH 14. This is nasty stuff. And there's a welded flange. So this flange here is welded onto the probe of the spectrometer itself. And then obviously we've got the mating T-piece here and a gasket in the middle. So there is absolutely no chance of that leaking whatsoever because it's hot caustic. But that is making a measurement every 2 minutes of their process. This is in a biofuels facility. This biofuel is making it's fermentation. They're making bioethanol. And there's a we call it the port tube. So you can see there's a little tube there that's welded onto this quick release sanitary fitting. So that can be taken off very quickly if need be. And this is in the recirculation pipe. So they're recirculating corn mash through this all the time, and it's constantly, again, making measurements and monitoring their fermentation. So they still take HPLC because the HPLC is, everyone's so used to doing it, it's what they do. But they use the spectrometer in between. So the HPLC is every 8 hours, but a spectrometer is every 2 minutes. So they use that to get kinetics, dynamics. They can spot problems before they happen. Bacterial contamination, have they added the right amount of enzyme, that kind of thing. And then the last one here, this is an edible oil refinery in the UK, where this is a probe, the same port tube as shown here, but it's welded directly onto the process. And then there are 2 seals here. There's a piston seal in the tube about here, and then there's a secondary seal where the locking nut is, just in case. And this is actually an alkali refining process being used to measure the FFAs and phosphorus to feed downstream into the process. So what does FTIR actually measure? I've given you a very, very rough outline of what it measures, but here's a slightly more detailed example. So one of the things about biofuels and renewable fuels and the conversion for this audience, predominantly of fats, oils, and greases into fuels, is there are a few different places they can come from. We've obviously got the plant-based fats, and animal tallow is another big one. And the contaminants are very different depending on what you're talking about. So I've chosen phosphates because phospholipids are effectively organic molecules that are part phosphate, part something else. And in animals, we have the degradation of DNA and the degradation of bone that produces phosphates. So I thought this was a good example to use in both cases. So firstly, this is a highly polarized molecule. As I explained earlier, this bond here is polarized, but so is this one, so is this one. So Raman wouldn't do a very good job of identifying this. They're also quite similar. This is just the phosphoric acid by itself. This is sodium phosphate, and this is calcium phosphate. They're very, very similar to each other. So NIR probably wouldn't be able to differentiate between them, but fundamentally it's measuring the same type of thing as FTIR. What the FTIR, in this example, I'm just measuring this bond here. So the PO single bond. In phosphoric acid, it's fairly easy to see. Phosphoric acid has a really strong infrared signal, really, really strong. When we add 1 sodium to it, that sodium binds to the oxygen. In reality, you've probably got a delocalized negative charge for the chemists in the audience, but for the simplest sake, I've just drawn it this way. And what that does is it changes the frequency of this bond. This is a spring. It's constantly vibrating, and bonds are made of electrons that sit between atoms. That's all a bond is. When you throw on this sodium, which effectively has a positive charge, it's sitting here, it's trying to draw the electrons out. So the electrons aren't sitting here so much anymore. They're being pulled over here. So the electron density drops in here, and that changes the strength of that bond, and it causes the frequency at which the bond is vibrating to shift, which means that spectroscopically, you start to see 2 different bonds as you add sodium. You see the original one you had for phosphorus, and then a new one start to appear because effectively it's a different bond, it's a different chemical. And then the calcium over here, which is calcium 2+, is bonded to 2 at once. So now we've got the electron density being changed further, partially coming down to here. The size of the calcium is different as well, so that has an impact. So sodium versus potassium, even though they're both monovalent, they're both 1+ charges, have different impacts because they're different sizes. And they start to physically push the bonds out the way and things get moved around. And then the calcium as well, we've got contribution here, but we've also got a contribution here, and that again changes the electron density. Trying to map these out with a piece of paper and a pencil gets very difficult very quickly. especially if you have different salts floating about in the same mixture. That's where the computer programs and the artificial intelligence I spoke about earlier becomes really powerful, because it allows you to measure those different things. All you have to do is tell it what you know is there, your sodium levels, calcium levels you might have got from an offline reference technique like atomic emission spectroscopy or atomic absorption spectroscopy. And at that point, the computer program then handles the rest. As long as you know that your fundamental technology and your validation are set up correctly, you can then trust the algorithm to do that for you. So example applications, what kind of things can we use them for? Fermentation, it is a biofuel. So I'm talking about it here. It may not be the key driver for most of this audience, but I will briefly talk about it. Fermentation, if you're making ethanol or butanol or other alcohols, or to be honest, anything that is fermented, you can measure the sugar, you can measure the acid, alcohol, and indicative chemical concentration. So with a yeast fermentation, you might want to measure glycerol. Glycerol is a stress hormone for yeast. So if your glycerol concentration is nice and stable, your yeast is happy. If your glycerol concentration starts to spike, your yeast has a problem. Maybe it doesn't have enough nitrogen. Maybe there isn't enough food for it to feed. Maybe the enzymes aren't working. That kind of thing can be flagged up quite happily. You can also look at the consumption of feedstocks like sugar so that you can make sure your process is efficient. We have one customer who thinks they've managed to knows they've managed to increase their ethanol by around about 0.1%, which doesn't sound much, but what I mean is they've gone from 15 to 15.1% ethanol in their final product, and that's for 1 million litres for 8 fermenters, and they have approximately 150 fermentations a year. If you do the maths on that, that is a very, very high return on investment. So that kind of measurement has big knock-on implications. Biodiesel. Now, I appreciate biodiesel may not have the future that renewable diesel has, but it's still a key player, and it's still around. In the UK, our diesel has biodiesel in. It's not going anywhere quickly. So transesterification, fatty acid methyl esters, free fatty acid concentrations, so you can track the progress, you can track the quality of what's being made. Do you have to take it back round the process again? Is your transesterification complete or not? You can also measure sodium methoxide and methanol concentration. So you can dose in your catalyst, make sure your catalyst is at the right concentration for the process. And you can do all of that with one measurement at once. And then for both biodiesel and renewable diesel, there's the pre-treatment, especially if you have dirty feedstock. If you've got animal tallow, is a good example. That's been through quite nasty processes. It's probably dirty. How long has it been stored? Has it started to go rancid? Has it got any metals in there that could kill your catalyst if you've got a renewable diesel process downstream? Being able to measure those, effectively, if you can prevent someone from destroying a catalyst, you've paid for any instrument immediately. So that kind of measurement is really important. And I've got some examples of that in a minute. And then downstream, you've got the distillation and blending. So if you've made sustainable aviation fuel and you want to make sure you blend it to the right concentration or the right performance, or gasoline or alcoholic fuels as well. Certain gasolines have alcohols in them. So blending that kind of thing, infrared allows you to measure that as well. You can do water, methanol, contaminants, but also vapor pressure, octane rating. Now, these are physical properties, but they're caused by chemistry and chemical concentrations. So again, artificial intelligence algorithms, we don't need to know exactly what chemical makeup causes the different properties. We can measure the properties, measure the spectra, let the algorithm do the rest, let it do the heavy lifting. Because we're measuring the fundamentals and the fundamental chemistries, we can let the algorithm do the work. You can probably do it with NIR, but you will always get a better result with FTIR. You'll get more precise and more accurate. So example spectra. This is a spectrum, this is for biodiesel, and this is a mixture of FFAs, FAMEs in predominantly sunflower oil. This was a laboratory example. So we've got this big peak here. This is the actual carrier oil itself. This is the C double bond O in the triglycerides. And then we've got this shoulder here. These are the C double bond O's in free fatty acids. We've got the double bonds in unsaturated triglycerides, FAMEs and FFAs. There's another one kind of around about here as well, just off to the screen. And you can measure things like iodine value as well. Probably not so useful for biodiesel or for renewable diesel, but in oil treatment, then that kind of thing, which can then feed into things like solid proportion at different temperatures or melting points, and that can all be useful. We've got the CH bends in FAMEs and FFAs. This is the CH bend in your triglyceride. We've got the carbon-carbon stretches, again, in the triglyceride. And then we've got some of the stuff in the free fatty acids in the FAMEs. And then the oxygen to carbon double bond oxygen bend in free fatty acids. That's a bit of a weird one to get your head around exactly what's happening there, but the whole molecule is kind of bending a bit like scissors on the hinge. And then we've got a different version of that in the FFAs and the FAMEs as well. You don't have to be able to interpret this to understand what's going on. You don't need to use that at all. You can let computers do it for you, but it's nice to know what's going on. It means when you're building a calibration, you know which area to focus on. You can throw away data you don't care about. That's the beauty of FTIR. You always measure the whole spectrum and throw away the bits you don't want. So you can do that. And it's just, it's another benefit of FTIR. Here's some more examples. So on the top left, this is a lab calibration of fatty acid methyl ester in sunflower oil. This actually comes from the spectra I just showed you. And these are examples. This is a calibration where the limit of detection, which is the root mean squared error of a cross-validated model, RMSECV, if you've heard of that expression before, it basically means what's the performance, what's the average error. And in this particular case, and the number does depend on the actual process you're using, but in this case it was 0.06. If we had a wider concentration range where we went up to 100%, the number would probably be a little bit higher, but not by much. This was about originally for contamination in triglycerides, but if you can measure down at the low levels, you can definitely measure the high. There is no maximum concentration for this technology. You can measure 100% quite happily. The same instrument with no dilution can measure 0 to 100%. That's one of the beauties of most spectroscopies. Not all, but a lot of them can do that. And then at the bottom, we've got FFA again, in sunflower oil. This is particularly relevant for things like biodiesel, where you need to know how much FFA is in there, because that's going to gobble up your catalyst. For renewable diesel, the benefit to being able to measure that is to look at total acid number, so you can predict the corrosion and the damage that will happen to your plant. If you can effectively integrate over the amount of acid you fed through it, you know when you're going to have to do planned maintenance and replace and repair things. And planned maintenance is a lot cheaper than unplanned maintenance. So being able to log that is particularly important. And then on the right here, we've got an FFA in it's actually in an edible oil refinery. What I particularly like about this is you can see the red dots are when they take a sample, and they were not taking them very often. And after half a day, after being installed, it was quite good timing actually, but after being installed, their FFA value crept up. And we don't know whether this was a changing the feedstock or whether they changed something else, but it definitely crept up, and it took them another half a day before they took a measurement. And they corrected, and they also overcorrected. And then it took them another quarter of a day before they took another measurement, realized and managed to dial it back. The spectrometer spotted it 2 minutes after it occurred. So this is a classic example of that sat-nav comparison I told you earlier. It was spotted very, very quickly, and they could have acted on it much, much faster. So this kind of thing, again, if you're feeding into something like a renewable diesel, you could be monitoring everything that goes in. You can have critical limits, you can have accepted limits, and the second you go outside of that, you can stop and you can deviate your product, you can change things so that everything ends the way you want it to. This is brand new, hot off the press data. We have only recently done this 2 days ago. This work was completed. So I'm delighted to be able to talk about it with you today. This is measuring contaminants in rendered animal fat, so tallow, like I was talking about earlier, and this has a future in renewable diesel. That's what this work was for. And we're measuring phosphorus, sulfur, calcium, and iron. The phosphorus is predominantly from bones in this particular setup, but there will be some phospholipids because animals do have phospholipids in them. There will be some DNA degradation, again, the phosphate backbone in that. And we can clearly see a pretty good calibration here down to 7.2 ppm. This means if this was installed on your inlet, either the outlet of the pretreatment or the inlet to the pretreatment, or both, you're able to measure what's going through, and you can make sure that the stuff you're feeding into your renewable diesel, into your Fischer-Tropsch, which is all in the gas phase, so the armadillo wouldn't be monitoring that, but we can measure everything that goes into it, so you can have confidence that your plant itself is not going to break, you're not going to destroy your catalyst or anything like that, and then you can also improve efficiency. Sulfur, a little bit more spread. Sulfur probably comes from quite a few different sources. You've got amino acids like cysteine, you've got other chemicals that could be in there with sulfur. So I'm not surprised it's a little bit more spread. But in this case, again, 12.4 ppm. With more data, we could probably tidy that up a little bit. One of the things about these algorithms is the more data you have, the better the results, because you can train it better. I should point out the phosphorus was actually a linear algorithm, but the sulfur was a curved one. Then at the bottom, we have calcium. Again, most of this calcium comes from bones, and it's probably chelated quite strongly with the phosphorus. They're not correlated. They are independent variables. So we are definitely measuring calcium or phosphorus, but most of it is probably bound to the phosphorus itself. 4.6 ppm there. And then iron. I suspect most of the iron comes from blood. It may still be in its hemoglobin form, which could explain why these results are so good, because we may actually not just be looking at the effect that iron has on other molecules, we may actually be looking at the hemoglobin particle, molecule itself, which is quite big and has quite a strong infrared spectrum. But you've got iron 2 and iron 3, you've got different charges there floating around as well. So this was quite a little bit tricky to build a calibration for, but we managed to do it. And 1.75 ppm. So those numbers mean that is the number at which we tell you it's definitely there. So with phosphorus, if it was 8 ppm, I would tell you there is definitely phosphorus there. If it was 6, I would have to tell you it's below LOD. I don't know. It might be, it might not be. You may have heard of something called an LOQ, limit of quantitation. That's where you're really certain you're measuring it right. And that's just over 3 times your LOD. So between 7 and 21 parts per million, I could tell you phosphorus is there. I'm not entirely sure how much is there. Above 21, I could tell you it's 21 plus or minus 7. That's how it works. Bear in mind, these numbers go up to 450. So 450 plus or minus 7, that's actually quite a nice error to be working with. So conclusions. Industry 4.0 is genuinely taking spectroscopy out of the lab and online, and it's fascinating and it's really exciting. It's a really exciting time to be involved. I really enjoy it. I can only see the future getting better and brighter, and being a part of it is fantastic. Biofuels and renewable fuels, they truly are at the cutting edge of science and technology. They are, it's not should be, they are leading examples. They're going to be a pivotal way in preventing and fighting climate change, and they will be feedstocks. I truly believe the materials of the future will be grown in a field, and then they will be treated, but it will be chemicals. So it will be things like the same molecules we make in petrochemicals, but we'll make them through this type of process. And static optics FTIR spectroscopy allows you to take the information that a lab instrument provides, but it gives you the robustness of something like a process and IR instrument that you can then use to make meaningful measurements that you can use to actually drive your process and improve your process for both biodiesel, renewable diesel, fermentations, any kind of biofuel process. There may well be ones that I've not even touched upon here that I'm not aware of. It's almost certain it will work. If it's in the liquid phase, then static optics FTIR, I'm hoping, should be something you would consider. That's me finished. So thank you very much for listening, and I hope there are some questions.
Thank you very much. That was absolutely excellent. So I will remind our audience that you need to type your questions in, because otherwise I can't see them. And while they're doing that, I will answer a question myself. I was very interested in your comment about the fact that you can see transitory species, things that you would not be able to see in offline analysis. And it seems to me that, particularly in such a complex situation as we have in biodiesel or renewable diesel production, I was wondering if you have any examples where you've found some new chemistry or people had some new insights in the way that their reactions work because they were able to see these more transitory materials that would have disappeared by the time they got it out into the lab analysis.
Yes, there's a customer I was working with recently. They produce vitamin, I think it's vitamin A, and that's chemically, that's a horrific number of reactions. It's like 12 different cascading reactions to do it. And the very first step is something called a Darzen's reaction, and they analyzed it for about 40 minutes, and they thought that's how long it took. From experience, that's, this is how long the reaction takes. We always leave it this long. And I said to them, okay, that's fine. Send me, I'll have a look at it for you and I'll let you know. And they couldn't get me any reference data because it was too fast. The reaction process was too fast. So I looked at it in first ab initio, looked at just the spectra, and ended up coming to the conclusion for them that they were 75% of the way through it, but not quite finished because they hadn't taken into account their transition states. And they had transition states they could never analyze because the second they took a sample offline, it disappeared.
Yeah.
And it's only by looking at it online that you could see it. And as a result, they now leave the reaction for an hour and a half and they get much better yields. So yes, that kind of thing.
We do have a couple of questions. The first one is, how many spectrum do you consider to have a usable model?
Good question. It increases with the number of chemicals that are present. So it's not the number of chemicals you want to analyze. It's the amount of stuff that's actually present in the mixture. Because the way that most calibrations work is you feed in a load of spectra and feed in a load of data, and it then you then build a model of what is important, what do I need to pay attention to, and what parts of the spectrum do I downweight and I ignore. So I have built robust and usable calibrations off of just 10 spectra because it was a relatively simple mixture and worked quite well. I've got one customer where I've had to use 400 spectra because their process is so horrifically complicated that you need that much. Now, a near infrared spectrometer would have needed 800 spectra. So it's still, but that's their process, not spectrometer. In general, it's about 30 to 40 to get most calibrations. And that's relatively achievable. If you think you're taking 3 or 4 samples a day, it's a couple of weeks. It really isn't actually that long to get something up and running.
Thank you. Yes. Next question. Is ppm the typical limit of sensitivity for trace components?
So normally I'd say yes. I have this morning, and genuinely, I know it sounds like I'm making it up as I go along. It was genuinely this morning. We completed some work where we were looking at arsenic in phosphoric acid, and we got to 13 ppb limits of detection, which for spectroscopy and FTIR is amazing. And that's a combination of things. It's got a very high, it's called extinction coefficient. So the spectrum is very strong for that molecule. Their reference data is top notch. So one of the things that compound your errors is an error in reference data. So if your titration is a bit erroneous, if your HPLC hasn't been calibrated very well, that error compounds the detection limit in the spectrometer. So their reference data is fantastic, and we're looking at a very narrow range of low concentrations. So in that case, we've done ppb. I wouldn't promise that for everyone, but ppm I'm comfortable saying we can almost certainly do.
Thank you. Next question. For products that use FAME as raw material, sucrose esters, for example, is it possible to use the IR Modillo to measure the consumption of FAME? Thank you.
Yes, 100%. You can measure that. You would be able to watch it consuming over time. You can then look at rates of consumption and kinetics, or if you're just trying to maintain a steady level of feedstock. So we have one customer who does something very similar, where they're measuring, theirs is a sucrose-fed fermentation, but they want to measure a constant or maintain a constant level of sucrose regardless of uptake rate. So whether you've got biomass growth or production, they want to maintain that. So they measure that, and that controls a feedback pump that doses to the same. But yes, measuring FAME consumption, easy, not a problem at all.
Excellent. Well, that's come to the end of the questions that I've received from the audience, and we're also getting on towards time. And so I'd like to thank everybody for attending this webinar, and thank you, Jonathan. That was excellent.
Thank you.
Thank you.